In this Canvas system, it doesn't put like a D or like get rid of the name, so I won't know until the final grades go in. And then when you try to put a final grade in, it'll tell you person's no longer part of the class. It's a,
Pretty silly system.
huh?
That's a silly system.
We used to get a notification when a person would drop the class, would be notified, I mean, by email, I think, for a while. And then if you looked on a sheet, their name basically would be either removed or read or something like that. But now, anything goes. And, well, I'm not sure what they're gonna do. They must be getting ready to put in a new system. At least that's what I think. All right, first, any questions at all? Now, today, I'm gonna do something, all right, I'm gonna start with, I believe it's problem 7-1, and then I'm going to do, actually, maybe I'm gonna start this way. I'm gonna start with problem 7.2.2, but there's a reason I'm doing this. I have to talk about some of the things, the properties of Fourier transforms and how they can be such a benefit right here doing these class of problems. And this is 7.2.1. By the way, do you want my book or?
I've got it.
All right. 7.2, I think it's .2. It's the one with the spectral energy density. And we're going to go through a whole bunch. First, I'm going to put the problem up. Then I'll show you, I'm going to do some background development here, and I'll show you something that will help you a lot on the final or the last quiz, because this can be confusing. So they give you a statement of a spectral energy density of X, and it's equal to 1 minus, and it's the magnitude of omega. And over here is it 8 pi?
Yeah.
8 pi. And what I'm going to put down is a normal way you express a function like this. If you want it only to be valid over a certain range. And for this, it's going to be valid from plus to minus 8 pi, isn't it on there?
Yeah.
So the way you would put it, and I'll do it this way. When you think of a function like this, if you had something where this is tau over 2, minus tau over 2, this is tau over 2, and the height is 1 here, this can be expressed as p tau of t, or as rect of t over tau. Either one of those two is an expression of that function. If this is t here, and this is the height. Y'all with me? I think everybody's familiar with the rect function, right? Either rect or the way it's usually expressed in a lot of work is p sub tau t, the width, total width of the pulse. So when you have a function like this that's going to be only valid from minus 8 pi to pi, that means this total width here would be 16 pi. And did y'all follow me on that? Everybody with me? So you can talk about this as either rect of, and in this case, it would be omega over 16 pi. That's fine to do it that way. And with that, you don't have to write another part of that, because that tells you the only place where this is going to have a non-zero value is when omega is between minus 8 pi and plus 8 pi. You always need 0 anytime else. That's an easier way to express it. And then they want a few things. They're going to ask some stuff. But before, well, what's the first thing they ask? The mean squared value or something?
Yeah, mean square.
So they want the expected value of x squared. Now the expected value of x squared can be found a couple ways. One is it's equal to Rx of tau, right? When tau is 0. Does everybody know that? You with me? It's the autocorrelation function evaluated at 0 is the mean squared value. With me? You can also get it by taking the 1 over 2 pi and integrating this function, Sx of omega, d omega. Don't forget the 1 over 2 pi either. That'll get you there. Everybody with me on that, class? Now this is the way that the solutions do it, but it's the harder way. And I'm going to tell you, I know you have calculators that can do all sorts of wonderful things, but oftentimes this particular function can be tricky because there's different ways of expressing certain things, and especially sinc functions with calculators. So I'm just going to show you some things. This is something I'm trying to do to help you. We're gonna take a look at getting this guy right here. We're gonna see if we can get that using some tricks. So first, there's several things I'm going to show you, but this is important. Remember, I'm going to build a little chart here. Matter of fact, what I'll do is this. I'm going to say we'll have functions x of t, and then we're going to have the Fourier transform x of omega. So for this, the first one is delta t goes to 1. That's a normal thing that everybody knows, right? You know, an impulse in the time domain at t equals 0, it's just constant, 1, period, all over the spectrum. The next one is going to be the rect of t over tau, or the symbol can be p tau of t. And do you remember what that one was? We did it once or twice in this class. We talked about it. Anybody? How many? Anybody know? Yeah, I won't ask you to repeat it. How many have an idea what it is? Begins with an S.
Is it a sinc function?
Sinc function, right. But the sinc function has this form. It's tau times the sinc of omega tau over 2. Now here's where you got to be careful with your calculators. That sinc function right here that I'm using is defined as the sinc of x is equal to the sine of x over x. That's the definition I'm using. There's a second and I'm going to explain why this other definition is used. Now, if you look at that one just for a second, and I don't want to digress too far. How many have seen this definition? You might not remember what definition. That definition is used, a lot of times it's the simplest and most common, but let me show you why they use a different definition. If you plot sine of x over x versus x, right? It starts at a value of 1. I think everybody sees that. Because at 1, just looking at it's undefined, right? But if you use L'Hopital's rule, take the derivative of the top, you get a cosine, derivative of the bottom, you get 1 with respect to x. Then you actually go ahead and evaluate that. You get 1 over 1. Cosine is 0, is 1 over 1, it's 1. That is the value. Then it goes down, and there's a 0 here. Keep doing this. It'll basically be a dying, like 1 over x function at that point. It'll have an envelope of about 1 over x. Y'all follow me, class? Where's this first 0 here? How would you get it? When I say first 0, it's where the functional form goes to a value of 0. That's what they mean when they say first 0. How do you get that, class?
Whenever sine of x is equal to
0. When is the first time after x equals 0 that sine x equals 0? Plus or minus pi, right? Y'all with me on this? So this would be a 0 pi, and this 0 would be minus pi. Now that's true for this function. We could find the next 0, which would be 2 pi, or minus 2 pi, and so forth. It's just something you have to be aware of. But what they do a lot of times, and this is true in this department sometimes, and I think they used to do it in signals and systems. Anymore, I'm not sure what definition. They use this definition, and they don't state it explicitly. They're going to say, and I'll just call it the sinc prime of x, and that's equal to the sine of pi x over pi x. Y'all follow me? Now how many have seen that definition? That one's used a lot. And here's the reason it's used. So you know why that definition is used. And your calculators may use this definition. MATLAB uses this definition. And that's why you find these inconsistencies when you're actually looking at plots and inverse solutions of this. Now just listen. So if you look at this function and you plot it, what do you actually get? Well, here's x, and now I'm going to plot this one. The sine of pi x over pi x. Well, at 0, it's still 1. If you take the derivative of the top, you get pi times the cosine pi x. Derivative of the bottom, you get pi, right, with respect to x. So you get pi over pi, it's 1. But where's the first 0 of this function? Where's this 0 right here?
When x equals 1?
When is sine of x 0 right after x equals 0? It's 0 at pi, right? Well, when does that occur? When x is 1. You see that? So the first 0 here is at 1, or minus 1. Next 0, 2, and minus 2. And that's the reason they use this definition, because the zeros are all at integer values. And it makes the calculations of a whole lot of things simpler because you don't have that pi term in it. That's the only reason they use that definition. Just so you know, but be real careful about that, because I've fallen prey to assuming they were using this definition. It's the most fundamental, but they were using that definition. And there's nothing they say explicitly a lot of times that they're using that one. That's the problem I have. So that's a little background on some of the stuff you have to be aware of when you're messing with these problems. And your calculators can really throw you off on this one. I don't even know what sinc function your calculators have. Matter of fact, that would be a good thing for all of you to look up to make sure you know what you're doing. All right, back to this. That's the first pairing I have to say. Second pairing is this, or the next pair you should know very well, or at least be aware of, is the triangle function. Now, the triangle function is really, I'm going to define it over here, but it's simply this. It's a triangle waveform like this, has a height of 1, with tau over 2, minus tau over 2, and it's a triangle, right? It's just like the rect function we had, only it's got a pyramid shape. It's a triangle. So the mathematical expression for this triangle, and I'll put it over here, you take a look at this function. By the way, has everybody seen that symbol used for the triangle? No? It's very common. I won't say it's universal, but that's the symbol they use. Now, the mathematical definition for that is simply 1 minus, and it's going to be 2 times magnitude of t over tau, and then it would be the rect of t over tau. Now, you look at that, and what that's saying is the rect t over tau tells you you have a width from minus t over 2, tau over 2, to plus tau over 2. You all follow me? Everything else is 0. And this is simply an expression that shows a pyramidal shape. At 0, when t equals 0, this is 1. When t equals tau over 2, just look at this. Tau over 2 times 2 is tau. Tau over tau is 1. 1 minus 1 is 0. It goes to 0 at the end. That's a linear relationship. Everybody got that? Now, the transform of this, I'm not going to go ahead and prove this, but the transform of this is tau over 2, the sinc of omega tau over 2. And again, I'm using this definition of the sinc function. I'm sorry, not 2, 4. And it's actually sinc squared. This is important. That's a legitimate autocorrelation function Fourier transform. This one is not, because it goes negative. See this? The sinc function goes negative in the frequency domain, and this is not a legitimate. It's flat on top if you look at the autocorrelation. If this was the autocorrelation, and I'm using t, not tau, but obviously you can replace t by tau. It's the transform pairing you need. Y'all with me on this class? Now, the next thing I'm going to show you, well, I could fill this up with some more transform properties, but here, transform pairs, but there's a property that becomes very, very important I'm about to talk about that we're going to use to solve that problem. that he doesn't talk about, but it makes life a lot easier in a lot of ways, is this. You remember if you had x of t going to x of omega, and there's something, and by the way, I should put this up here. When I'm talking about x of omega, I'm saying that is the integral from minus infinity to infinity of x of t e to the minus j omega t dt. And if you wanted x of t and you had x of omega, it would be 1 over 2 pi, an integral from minus infinity to infinity of x of omega times e to the plus j omega t d omega. You remember these pairs? The Fourier transform pair, you almost have to know like Ohm's law by the time you're about to graduate, because it's going to be used extensively in many of your courses. You're going into communications, that stuff is just there all the time. You all with me on this class? In Fourier series analysis you're used to. I think you should remember that. It's the standard common definition for Fourier transform pairs in the omega domain. Now, you may have used the F domain, but this is the much more common way. And remember, omega is just 2 pi F, right? So if you use the F domain, if that was an F, and that was it would be 2 pi ft right there. And this would be 2 pi times df right there. And therefore, the 2 pi's would cancel. You'd see that go away. But I'm going to tell you, that relationship right there is typical. Now, if you have this, and here's where it becomes real important. If we know we have a transform pair, x of t goes to x of omega. Now, this is a capital X, by the way. Then if I take this functional form, and I'll give you the demonstrations, x of omega over here, you ready? Now, it doesn't matter what it is. It could be a sinc function, it doesn't matter, sinc squared, whatever it is over here. I take that functional form and I replace the argument omega with t. And you can call it capital X of t, but now we're back in the time domain. You all with me? We take whatever that function is, if there's an omega, we replace it with t. And we can prove, if you want to see it proved, I'll prove it for you after class. You can prove that now that will have a transform on this side, which will be equal to 2 pi times small x. It's this function now, whatever the time domain function is. But instead of t, you get minus omega. Now, that is a property of duality. Have you heard about this? Do you remember this from Signals and Systems? This is a real powerful property, because you can solve a lot of Fourier transforms that have no closed form solution in the time domain to frequency by using pairing, and I'm going to show you one. And then I'll show you why that's so important for what we're doing. And this is kind of neat. I'm going to erase this if you don't mind. I want this part of the board. I want just appreciate this. So if I have a DC term in the time domain, this is x of t, and this is the transform I want, x of omega. And I have 1 in the time domain. What? That's DC, right? 1 volt, on forever, been there forever. What's it in the frequency domain? Well, right off the bat, the way you would normally think about this, first time thoughts at least, would be, well, the transform of that, the frequency domain, would be the integral of 1 times e to the j omega t, right, or e to the minus j omega t dt from minus infinity to infinity. Y'all have heard that? I mean, that's the formal definition, isn't it? You put in the functional form x of t, and then you go ahead and multiply by e to the minus j omega t and integrate it dt. Now, what's the integral of that? I'm making a point here, let's see. Well, e to the j omega t integrated, you get 1 over minus j omega, right? And then you get e to the minus j omega t evaluated from minus to plus infinity. So you get e to the minus j omega, and it would be, think of it as infinity, minus e to the minus e to the, it would be plus j omega infinity. Can you all follow me? This did the integral and evaluated, right? What's that value? Anybody know? Now, normally you would put a t here, right? I put omega, and in the limit as t goes to infinity. You all follow me? But what's that doing? What is j omega t doing as t gets larger and larger? It's just one that's spinning around the unit imaginary circle. You have a real and imaginary axis, right? You all follow me on that? It's called undefined. It's not defined. There isn't a closed form transform pairing of this. In higher level math, when you get something like this, they will prove that this goes to what I'm about to show you. You all with me? Now, let's use duality on this one. And I know this, so listen to me. I'll do it right here. What does delta t go to in the frequency domain? Class? 1, right? Y'all see it up there? 1. All right. Now think about what I said with this property of duality right here. Delta t goes to 1, right? Following? All right, so I'm taking this functional form 1 and I'm putting it in the time domain. So I'm using duality, so I take 1 and I put it here. Now, in the other domain, you have to multiply by 2 pi. You with me? And then I take the functional form in the time domain and I replace the argument t with minus omega. And I have a comment here. Everybody follow me? Now, you might remember some of this now. And I got a question for you. When does that delta function turn on? In other words, go to a non-zero value. At omega equals, or at minus omega equals 0. So that negative sign can be done away with. You can make it that. And guess what? That's the right transform pair. 1 goes to 2 pi delta omega. And the way I got it was not by doing that, because for you to solve that one, that is a mathematical nightmare kind of deal. I mean, that's a higher level math problem. They spend years figuring out ways to prove certain craziness, all right? But that, nevertheless, this is true. You all with me, class? Basically, the argument goes something like this. If you take a look at this, as t goes infinity, these things are spinning faster and faster and faster and faster and faster. And eventually, what happens is they're going to come together. By the way, this right here is minus sign. That's a minus sign of omega t over omega. It's not omega t, it would be a single function. But anyway, it's a mess to prove that. This is the easy way. You all with me? Now, how many at least follow my thoughts on this? You're going to see why I'm still. You with me, Riley, or you having a problem? I mean, you remember signals and systems. Mm-hmm. There's 3 courses that are core. If you don't know these things, you're really going to get killed in higher level courses. One is circuits. You got to know how to deal with R, L's, and C's. Transient or steady state. You have to. You'll never pass out of the engineering program unless you do. The second is signals and systems. You have to know Laplace. You have to know Fourier. You have to know all that stuff, and you should know Z-transforms by the end of it, because some instructors don't cover that, but that's real important. Z-transforms, and to be frank about it, there's other subtleties in there. The DTFT is very important, but that's something you become aware of how important it is in your courses. Now, you're going to take controls, right, everybody in here? You're going to find out in controls how important signals and systems is, and I think Matthew Kirshner's the guy who teaches controls, I think, unless somebody else, and he will do a huge amount of stuff relying on these kind of things, properties like this. So now back to this problem that I was talking about. And you'll see and understand why it was so important. So I look over here, the spectral domain, and I made the comment early on, if we wanted to know what the mean squared value was, we could take that function and integrate it, and we'd have to integrate this thing from minus 8 pi to plus 8 pi, right? And that's doable. That's not a hard function to integrate. They can be very hard. I promise you, some of the functions, the integrations get really tricky. But I know one thing. That's a sinc function. Y'all follow me on that? That right there, I'm sorry, this is a triangle function. That's a triangle function, and it's in the frequency domain, right? I just put up the property of triangle function in the time domain going to a sinc squared function in the frequency domain, right? Now we're going to use duality. Just be attentive here. I'm going to use this principle right here. So first thing I'm going to do is take this functional form, and I'm going to put it in the time domain over here, and I'm going to replace omega with t. Now I'm not putting a tau in yet, because you'll notice there's a tau in that argument. The tau comes, though, that's the last thing I do. So I come over here, and now I see that tau over 2 times the sinc squared of, and now it's t tau over 4 would be in the time domain, and the transform of that in the frequency domain would be equal to the triangle, or 2 pi times the triangle function with the argument of minus omega, and the width of it would be tau. Just take a look at that and try to convince yourself of what I'm showing you. You with me? John, are you with me on this one?
Yeah.
I mean, can you see it, David, back there? I gotta make sure. Now, it's still, I'm not real comfortable with that. What can we do with that minus omega? Think about the delta function argument. When does that triangle function have a p? First, is the triangle function an even function? How's that? How many see it's even? If it's even, it doesn't matter what this is. So make it plus. Don't think it like minus, because you can probably confuse the heck out of yourself if you're not careful later. As a matter of fact, I'm just going to erase that. So now I have that relationship. Now I'm going to do one more thing. I see over here, this function I can really represent as simply a triangle function, right? And the width of the triangle function would be 16 pi. And that argument would be omega. Do y'all follow me on this, class? Can you say it back there?
Yeah.
You follow me what I'm thinking here, right? This is a mathematical, yes sir?
This might be from a while ago. Why do you include that rectangular function?
That prevents any value outside that area to be 0, right? The rect function is only going to have a value 1 from minus 8 pi to plus 8 pi, because that 16 pi is the total width, right? And outside of there, it's 0. Now, if we didn't put that there, then this thing would have values for all omega. You with me? So think of this as just snipping it and having non-zero values over that window where the rect function is on. That's the only thing you need to think about. You with me in class? Now, going back to this thing. You'll notice the coefficient there is 1. Yes?
How did you see that the front part was triangular again?
This part?
Yeah.
If you just plot, follow me on this. Just look right here for a second. When omega is 0, what's the value of this function? 1, right? When omega is a linear relationship. It's not omega squared or omega cubed. It's just omega, right? So it's linear. Now evaluate this when omega is 8 pi. 1 minus 8 pi, it's going to be 1 minus quantity 8 pi over 8 pi. 1 minus 1 is 0, right? Goes to 0. Go the other way. All right? What's the value when it's minus 8 pi? Minus 8 pi, magnitude is still 8 pi, over 8 pi. It's 1, 1 minus 1 is 0. It's basically a taper, a linear taper. 1 to 0 at 8 pi. With me, class? That's the reason that is a mathematical description, that triangle function. All right, back to this thing. What I'm going to tell you is the coefficient up here is 1. So I'm going to divide both sides by 2 pi, and now I get this. If I divide by 2 pi, I get 4 pi over here. Does everybody understand what I'm doing? I'm trying to scale that thing so it looks just like this. Now I'm almost there. Are you with me? Take a moment. There's one thing I need to do though. The tau in that equation is 16 pi. Can you all see that? So if that's 16 pi, I'm going to leave this here, and I'm going to write that over here. If that's 16 pi, then when I do this pairing, when I have tau equal to 16 pi, I'm going to put it right here. Now you can see that part is going to be 16 pi over 4 pi, or 4, right? So I'm going to have 4. Then I have a sinc squared. And now tau right there is 16 pi. Can you all see that, class? So it's 16 pi divided by 4 is 4 pi. That's 4 pi t. And on this side, now it's going to be a triangle function of width 16 pi of omega. Are you with me? Everybody? Do you see? Now, why did I do that? Well, here's why. This right here is the spectral energy density that he started with. That's S of x of omega, right? Correct, class? And now if we take this function right here that we've got and we replace the t with tau, because that's what it really is. All right? We're in the time domain, so tau would be the transform. The tau that's in the autocorrelation function would be the thing you transform out. And that means this just becomes tau here. Or this is the autocorrelation function. This is Rx of tau. Are you with me? Now here's the reason I did all that. I spent time developing the thought process, making sure you see with Fourier transforms the relationships. Now because of that, here's what's nice. I got the autocorrelation function, right? Way back in the beginning, the question was somewhere, what is the mean value, or mean squared value, of the process? Wasn't that part A? So for part A, what they want is the mean squared value of the process. And that is the autocorrelation function evaluated at 0. And what is this evaluated when tau is 0?
4.
Yeah. What is the sinc squared? Sinc squared of 0 is the same thing as sinc of 0, right? It's 1. It's 4. And what's the answer? 4. Right? Now, they did it by integration. You all with me? You can do it by integration. You can take that function right here, and you simply integrate it from minus 16 pi to 16 pi. And then you have to divide the whole thing by 2 pi. In some ways, it might be easier because you can just draw a picture of a triangle, like so, and I'll show you how I would do this. I got minus 8 pi and plus 8 pi here. The height is 1, right? And what they want to do is integrate that over the entire thing. Well, I know that's a right triangle and stuff like this. I can basically just take the area right here, or right here, right? That area is 8 pi times 1. Do you agree with that? Follow me on this, class? So I could say 8 pi times 1 is 8 pi. And then I could say I have 8 pi over 2 pi or 4. You can get it that way too. But the reason I'm using this example more than any, it's a lot easier many times to get the inverse transform and evaluate. You follow me on this? Okay, you guys, we're missing some people. I wish they were here for this, and I hope they look at this lecture because this can be handy. Now, there's a couple other things. A couple other autocorrelation functions and spectral energy functions that can be kind of a nuisance, a problem. And let me give you another. Oh, let me finish this problem. What is part B to this?
There's only the one part.
Okay. Now, if for whatever reason, they say they want the amount of power in a certain band of frequencies, like from 0 to 1 hertz, follow me on this, or 0, say, pi hertz, then you would have to integrate from minus pi to pi. You always have to do it over the plus and minus frequency range. You all follow me on this, class? Sometimes people will just do over one, you might say just the positive frequencies, and you're going to get hurt because you forgot the negative frequencies. Even though there's no such thing as negative frequencies, the transform shows a minus omega and a plus omega. With me on this, class? So be aware of that. Another one, since there's no part B to this one, I got a question for you. If you saw, maybe I shouldn't ask this right now. You haven't really messed with this. That right there, probably doing the integration in the omega domain is easier, just because you can look at it and tell what it is. Here's one maybe not so easy, especially when you're talking about, like, you can add some more oddities. If you think about this relationship, if I have e to the minus a, I'll call it magnitude of t, I could use tau. Do you remember what the transform of that was? Anybody? If you don't worry about it, I'm going to give it to you. Well, the transform of that is going to be 2a over omega squared plus a squared. That's the transform pair relationship. Now, if you replace that t with tau, that's a legitimate autocorrelation function. Are you with me? However, they'll give you spectral energy densities, or spectral power densities that look like that with a scale factor. Are you with me? And they'll ask you for the total power. As a matter of fact, I think I have one of these. Do you remember which one this is? I'm trying to remember. There's one of them that did you guys try the problems at all? No? Oh gosh. These things are going to kill you if you don't get them. It'll take you more than a day to learn how to do some of these. Let's see. Not 6 to 8. Oh boy. Take one look. All right. Let's take a look at exercise 7-2.2. And you should make sure you know how to do exercise 7-2.1. We talked about it on Friday, but do you have that one, Alex?
Yeah, I can pull it.
My phone here. I'm going to erase this and put it up. And I'm going to leave that one there. So, for this exercise, 7-2.2, isn't that right? All right, give me the specifics.
Spectral density of omega is equal to 24 over omega squared plus 16.
Okay?
Find the mean square process.
All right, so they want the value of the mean squared value of that process, right? So that one's a little trickier to integrate, right? You can do it, but the formal way, the way you do it in the frequency domain would be what? Integrate Sx of omega, d omega from minus infinity to infinity, and then divide it by 1 over 2 pi, and that would be the value of x squared. It would be the mean squared value, right? Do you agree with that, everyone? Now, can your calculators do the integration fairly easy? I don't know, I assume they can. Why don't you give it a try, just to prove yourself? Because here's where mistakes happen at rates that are alarming. This always bothers me because I'm thinking, I wonder if air traffic controllers use calculators and stuff when they calculate collision times and stuff like this to have to suggest a different pattern. While you're doing that, I'm going to go ahead and do something. I'm going to call this constant K over here, and now you'll see why I did it. I'm not just doing this for my own sake, because you're probably going to see this kind of thing, but here's where mistakes happen. I can't make you guys not use calculators on this. But doing that integration is possible, matter of fact, very doable without calculators, but if you haven't done it in a while, it'll take you some time. Anybody?
I got like 29.6.
What is it?
I got 29.6.
Anybody else? There are no. I don't know the answer.
I had 3.
3?
I also got 3. Did you divide by 2 pi?
Mm-hmm.
3? These are possibles. 3? I'm making a point here. I think I've already made it, but what'd you get, Riley?
I think I'm integrating over the wrong bounds. Is it from negative 8 pi to 8 pi?
Negative infinity to positive infinity should be the bounds. What'd you get?
Infinity.
3.
3? You got 3? Okay. So 3 twice. Anybody else? There's.
Mine can't do infinity, big bounds.
Yeah, that's an interesting point to note.
I made sure to say, no, I actually wanted that pi in the denominator for the 1/2, and now I also got 3.
Okay, getting better. Anybody else? 3 is probably the answer, I don't know, but I'm about to go ahead and do it the other way. But I promise you, you'll make errors. Almost guaranteed with these kind of integrations, people make errors. The big problem is this: when you get absolute values, and if that omega is like to the 4th power, then things get buggy and weird. I promise you that, okay? Now, what I'm going to do is use this pairing principle that I showed you, duality. So over here, I can see that I want to make sure I have this of that form. When you look at this, somebody can see that a squared is 16 if I want to use that form by looking at the denominator. Y'all see that? The 16 is omega squared plus a squared. So if 16 is a squared, a is 4, right? A is 4. Actually, it's plus or minus 4, but 4 is good enough for anything we need to know. Now, if that's the case, then I know if I have 2 times, if you look at that, the relationship, get rid of the k for a moment. If you have 2a, if a is 4, that's 8. So I know if I have 8 right here over omega squared plus 16, that would go to e to the minus 4 magnitude of tau. That would be the relationship. Can everybody see that? Just by using, forget about the k. How's that? Put it up. Because we know 8 is 4, 2 times 4 is 8. 8 over omega squared plus 16 would go to minus 4 times magnitude of tau. Can you all follow me on this, class? All right. But it ain't 8. It's 24. So now I have to take both sides and multiply by 3. Are you with me? I'm making sure you all see. Well, what is this? That is the spectral energy, or spectral power density of omega given. And this would be the autocorrelation function. And therefore, if we have the autocorrelation function, a mathematical statement of it, we simply evaluated at tau equals 0 to get the RMS value. And you can see it is 3. Can you all see that? So in fact, it would be 3. And 3 is the right answer for this one. What's part B?
Find the mean square value of the process in the frequency band plus or minus 1 hertz centered at the origin.
Now, this one you would have to do an integration of. You can't use the autocorrelation for this. You with me, class? Could you try this on your calculator? So, belabor this point, but it's an important one. So use this, right? And now we want to take 1 over 2 pi. We want to integrate from over the band of what frequencies?
1 hertz.
So 1 hertz in the frequency domain is minus 2 pi to plus 2 pi. Remember that. 1 hertz in the omega domain is 2 pi, right? You have to integrate over the negative frequencies from minus 2 pi to plus 2 pi of that functional form, which is going to be 24 over omega squared plus 16 the omega. I want to see what the answers are.
I got 1.917.
That sounds right to me.
I also got 1.9.
Anybody else? I promise you mistakes are made. The 1 hertz is the thing that throws people, especially if they miss this class. You get that? I think that's the answer, by the way. All right. Another part?
No, that's it.
Okay. I'm glad I got that. I wanted to get.
And you said this was finding it over like 1 hertz?
Just 1 hertz. So 1 hertz is 2 pi radians. So minus 2 pi to plus 2 pi. You can't go just, I mean, theoretically, you could do it this way. You could go from 0 to 2 pi and just multiply by 2 here, because it's symmetric. That's one way to do it. Just be careful about this, because there's a lot of things you can easily mess up on these kind of things. I like the autocorrelation function. Even though a lot of you haven't done Fourier transform work in a while, you're going to be doing a lot, and some of the problems are made a lot simpler with that. Did anybody do exercise 7-2.1?
Yeah.
That's an easy one, based on what we just talked about. It's a simple integration over a defined band of frequencies, but it at least exposes you to calculating it. Now, there's properties in 7.3 that, frankly, a lot of this stuff is very, very obvious. I'm not worried about that. Got a couple other things to cover. So I wanted to get that out. I'll tell you what, spectral power density. You don't see the real importance of it now, but you will in the actual classes to come. A lot of things you're going to see that are important. Okay, got that. exercise chapter 6-8.1, because that one on a test or a quiz can really fool you. Well, I shouldn't say fool you, but you can get very confused if you're not familiar with it. And now I might as well ask you, 6-8.1.
You said exercise?
Yeah, exercise, and I think they have like noise. So they have noise in the time domain, and it has an autocorrelation function equal to like 10e to the minus, here I forgot.
2 magnitude.
What is it?
2 magnitude tau.
Okay. And then they have a process x of t, right? What is it equal to?
It's equal to a, which a is a random variable that has a mean of 5 and a variance of 2.
So sigma squared of a equals 10. And that means what? The mean squared value of a is 10 plus 25 is 35. So, everybody with me on this? Now, I haven't talked a lot about this, but noise occurs all the time, in everything. Thing about noise is it's uncorrelated. There's no correlation between prior values of noise and future values in the time domain, which makes it nice. It's also something that is uncorrelated with any information that's being transmitted or processed. And the problem, I think he says, x of t is independent of the noise, something to that effect. Now, it doesn't necessarily have to be, but it is, almost always. There's ways where if you have squaring operations, the noise will infect the squaring operation. If you have like x of t plus noise, the value of the noise at an instant time, you square it, then you can have factors that it could be correlated to. But down here, the simple problem, you don't have to worry about. So the part A is what?
Find the autocorrelation function of the sum of these two processes.
All right, so they're asking for Rx of tau. Not X, pardon me, Ry. I got to be clear. Or R, I think he used a Z, but I don't remember.
He uses it.
So we'll call it RZ of tau. First I have to define the actual value. So he's going to say Z of t is equal to X of t plus N of t, the noise. It's additive, basically. The noise is added to the signal X of t. Now we just we used the autocorrelations definition. And I'm assuming this is wide sense stationary, so I can do this. The expected value of, here it's going to be Z of t times Z of t plus tau. You all understand that is just a fundamental definition, right? There's nothing here that's tricky. If you look at that, that's really the expected value of quantity x of t plus the noise of t times the quantity x of t plus tau plus the noise of t plus tau. Now I want to tell you one other thing. In the real world, noise is not correlated to noise, almost always. There are certain exceptions that I'm really not familiar with and I don't like talking about. But since they give us an autocorrelation function of the noise, at least for small values of tau, it is correlated. You all follow me in this class? Which is troubling to me, but nevertheless, because they're independent, you're going to see things become very easy. Y'all know what I'm doing there, right? All right, now you got 4 terms. If you break this out, you're going to get the expected value maybe I don't have to be this formal, but when I take this times this, some of you probably already see it. That's the first term. Then it would be the expected value here. And I'm going to take the inside term, so the expected value of the noise times x of t plus tau. Then the last term, which is going to be plus the expected value of x of t times the noise of t plus tau, plus, finally, I get the expected value of the noise of t times noise of t plus tau. Y'all follow me? The only thing I'm doing is just breaking it down, breaking it apart, tearing it apart so I can evaluate each section. And then, by definition, we'll get to this in a second, what is this part, by definition?
Autocorrelation.
Of x, right? So it's going to be the autocorrelation function of tau. The next value, and this is a point I've got to make. I want to make sure I get your attention here so I can make it clearly. I have a value n of t, and I have a value x of t plus tau. But the statement at the beginning is x and n are independent random variables. That means it's the expected value of the first times the expected value of the second. You all hear me? The expected value of the noise is 0. And he says that somewhat. What does he say about that? You can get this way. Take a look at this. You know, if this is the noise, right? Take a look at this. If we wanted the DC value or the average value, you take the limit as tau goes to infinity and see what remains. That would be the average value squared. You with me, class? Well, what does this go to at infinity? Tau goes to infinity. It goes to 0. There is no average. It's the average value of that process is 0. Can everybody see that? That means when I take the expected value of these two because they're independent or uncorrelated, it's really the expected value of the noise times that expected value. The expected value of the noise is 0. So it goes away. Same deal here. They're independent, uncorrelated. Expected value of x of t may be something. Expected value of the noise is 0. It goes away. It doesn't matter if it's noise, t plus tau, or just expected value of the noise. So these two get canceled. Finally, this one is
Expected the
autocorrelation of the noise, right? So that is going to be plus, and I'll put it here, the autocorrelation of the noise of tau. And that would be RZ of tau. Now he asks, does he ask for what, the mean? What does he ask for?
Just the autocorrelation of some process.
Okay, now here's something I gotta say. For this process, he defines x of t as a constant a, no matter what. You all follow me? You'll notice there's no function of time in there. Can you all see that? This is a real important point. So if there's no function of time, that means the autocorrelation for that thing is just going to be that. It's going to be the mean squared value. Can you all follow me on that? Can you hear me on that? I mean, this is not a function of time. If there was a cosine of omega t, it'd be much different. Then you have to go through the process of tearing a cosine apart. You with me? And getting a function of tau. But because of that, this part right here just goes to 35, and it's plus 10 times e to the minus, what was it, 2 tau. And that should be at least, the autocorrelation of the process R, or of Z of t. And I think he has that, but I don't remember exactly how he has it. Now, if you look at that, obviously the peak, just take a look at this for a second. I've got a question to ask. You look at that right there, the value at tau equals 0 is 45, right? Can you see it? And the minimum value it has is 35, right? So the range of values is from 45 to 35. Then he asks a question, it's kind of silly, but he says how far, or what value of tau will make, see, how does he work?
Find the value of tau at which the autocorrelation function is within 1% of its value at t equals infinity.
Okay, what's the value of t equal infinity? Right? So we got 35, and he wants 1% of that, right? So 1% of that would be 0.35. Do you agree with that? Now he says, what has that?
Find the value of tau, find the value of tau at which the autocorrelation is at 1%. So at 0.
There's no value.
Never
Read
considered.
that again. I think we missed something.
Find the value of tau at which this autocorrelation function is within 1% of its value at tau.
Within 1%. That means
So within 35.35?
within 1% of its value at t equal infinity, right? So that means at t equal infinity, the value is going to be 35. If it's in 1%, it's going to be, at infinity, it's a minimum. So you're going to add that value to basically, you're going to say this. You're going to have 35, that's the value at infinity, and 1% added to there is going to be 1.01, and that's going to be 35 plus 10 e to the minus 2 magnitude of tau. So divided by 35, you get 1.01 is equal to 1 plus 10e to the minus 2 magnitude tau divided by 35. Take that to the other side, so you get 0.01 times 35 equal to 10 e to the minus 2 magnitude of tau. Okay, so that's going to be 3.5 divided by 100 is equal to e to the minus 2 magnitude of tau. So you're going to have a log. So, where's the pain in the butt? You're going to have minus the natural log 3.5 over 100 divided by 2 should be tau, I believe. What is it? I don't know. It's kind of a dumb way to ask him the thing. What he should have said is, when is the value of the autocorrelation function x? But he chose to add the percentages and stuff like that.
1.676.
1 point,
676.
anybody else? Is that the right answer?
Yeah.
The problem is the wording. Now, slowly, read that, ask again.
If the autocorrelation function of the sum is observed, find the value of tau at which this autocorrelation function is within 1% of its value at tau equals infinity.
So it can only go up. That's the reason I multiplied by 1.01 times 35, because it's gone up. And now you got to evaluate the whole autocorrelation function and see where that value is. You with me, class? There's probably more clever ways to do that, but that will get you there. And I got to ask one other thing about this. Or mention one other thing. There's a lot of subtleties to these things, and I'm just warning you. There are the hardest problem, in my opinion, hardest exercise, most difficult conceptually to see, even though when it's apparent to you, it won't be bad. I put the solution for this on the board, but I wanted to make sure I really drive this point home, is, it's an exercise. Hold on. Hold it for this one, and I know it's so important. This one, the diode. Did you look at these last time? Or not?
Is it the halfway rectifier?
What's that?
Is it the halfway rectifier? Sir?
Yeah, which one is that?
6-8.2.
All right. This is the tough one. We did 6-8.1, I think, right?
Yeah.
All right. 6-8.2, the exercise. They have a simple voltage divider, and they give you, they say that it has a sample functions of amplitude plus minus 12, and TA equals really 10 milliseconds. So the autocorrelation for that, if you look back at when you have that random process, it's just jumping up and down, that's going to be equal to 12 squared, or 144 minus tau over 0.1 or 0.01 squared. And it's applied to that half-wave rectifier. Now the problem is the signal in the beginning is going from plus 12 to minus 12, and you know the voltage across the output of a diode, I'll sketch it next time for sure, is only going to have a voltage when the diode is forward biased. Do you exactly follow me on that? Anybody look at this one? I just need to sketch it and you can do it. I know I'm already out of time, but this particular problem, it's not straightforward. It requires thought. And I put the solution up there. Did anybody look at the solution in OneNote for this exercise? I made sure I put it up there. Can you see if you can find it, Alec, on OneNote? It's the solution.
Yeah.
It is, there's a lot of ways to do this, but there's no like transform trick you can do. If you wanted, there's a trick you can do in the spectral energy, but it's very hard to do this in the spectral energy domain, as far as I know, without some fairly complicated tricks. But here, you have a process. It's plus or minus. Just let me finish this and I'll get you out of here. And you got two resistors, same value, R. You got a second resistor here, value R. And here's your output, plus or minus Y of T. Now, if you look at this signal x of t is doing this. It's basically jumping this way. It's going from 12 to minus 12. This is x of t. Now the output y of t, to get a picture of it, is doing this kind of stuff. It's jumping from 6 volts to 0, and then back up to 6 volts. But it's not going down to negative 6. Do y'all follow me in this class? So when you look at what this is doing, y of t, and you're talking about the autocorrelation of that, the autocorrelation of this function right here, Rx of tau, is going to be 12 squared, or 144. Then it's going to have, I could put the triangle function here, but it's really going to be equal to 1 minus the magnitude of tau over Ta, and that's true, and I can put down just a rect function of tau over 2Ta. But this functional form has half the magnitude, but it's not going from positive 6 to minus 6, or it would be just half that. Follow me? And because of that, it's going to have, if you look at this autocorrelation function, as tau goes to infinity, it's 0. Do y'all follow me? It has, this function has 0 average value. That function has an average value of 3, if you look at it. Y'all follow me on this class? I'd like you to try that problem based on what I just sketched out. See what you get. You know what you're going to probably have. You're going to have 36 as the magnitude for this. You're basically going to have a magnitude of 36, but you're going to have a few other things. You got to see how the form of that solution in there? For, because I don't remember actually. That's why.
And then you have just the output on the
Yeah, but I think, let me show it here. I'm just wondering if he does. Yeah, he does. He gets cross correlation. The autocorrelation is going to have 36. What is the time frame on that? The answer, the solution has a wrong answer. It should be tau over 0.01 in the second part. Yes, 36. Then it's going to be 1 minus magnitude of tau over Ta, whatever that is. And it would be the rect function here, but there's going to be the value of the process y, the average value of y here too. You give it a try. We'll pick that up next time. All right, now I posted the solution, but I'm telling you this is a tricky problem. A problem like this in a final can really cause you some brain damage or on a quiz. Make sure you give it some thought, because that one's tricky. I love it. All right, and please do that last